Good afternoon. My name is Joeri, and together with Boris, I will briefly explain some details about our measurement system, the Elgas platform. And in this presentation, we will go from sensor to cloud. The main goal of this project was to improve the health of the ship crew members by continuous monitoring the exposure of air pollutants in accommodations of ships, and also evaluating and communicating with the self-designed risk index and proposing some concrete remediation actions. To obtain this, we have built an Elgas measurement system, Elgas measurement platform that consists of low-cost sensors and also some data collection and storage and data visualization. And in this presentation, we will focus on the sensor part and also on the cloud part. This is mainly the architecture of the system. It consists of two parts. It's mainly the Elgas sensor box and a cloud part. And there is, in our case, there is a wireless communication between the sensor box and our cloud service. The communication inside this project is provided by Telnet, and cloud service is provided by Altingstock. There is also an option to hook the system into the local network of a ship and to get some that we also can communicate over a different communication channel. Let us now go briefly into the different blocks of the Elgas sensor box by starting with the Elgas sensor shield. So I hand it over to Boris.
Thank you, Joeri. Can you hear me?
Yes.
Okay. So as Joeri mentioned, the system, the box itself is divided in two parts. One is the sensor shield. We call it sensor shield. And the other part is the processing, which Joeri will explain a bit later. So I'm focused only on the sensor shield for now. So for the project, we selected roughly 11 relevant parameters, for which we selected also relevant sensors, relatively low-cost sensors. And this is a list of them. So we have 6 electrochemical sensors for nitrogen dioxide, carbon monoxide, nitric oxide, ozone, and so on. It's on the list. 1 PID sensor for TVOC, total volatile organic compounds. 1 optical sensor for particulate matter. 1 also optical, not dispersive infrared sensor for carbon dioxide, and temperature and relative humidity, which are resistive and capacitive sensors respectively. All of this, we also, during the project, we designed the so-called sensor shield, which is one board essentially, where all the sensors are mounted to form some kind of sensor array. The board also provides all the electrical power to the sensor, drives the sensor, and also acquires the signal from the sensor. So everything is built into this board. The idea of having this modular system as separate from the rest of the system is to be extendable. So technically, we can with relatively easy, we can modify the system with another number of sensor or another type of sensors. The sensor shield in this case is built around 5-volt architecture based on AVR. All the logic is based on AVR microcontroller, and all the data are communicated with the rest of the system using standard UART communication protocol. This is the schematic. As I mentioned already, all the logic and all the driving and acquisition of the signals is built in this sensor shield. And this slide represents overview of the algorithm that is taking place, all the logic which takes place inside the sensor shield to acquire the signals from the sensor. So in general, we have two types of sensors: the sensors with analog output, so it's simply voltage difference, and the sensors with digital output. That's why we have just two streams over there, let's say. So all the sensors are controlled by the sampler. So we have sampling rate, which for in this case is more than 10 samples. But I just want to clarify that this sampling rate for the sensor in the base of the sensor shield is the frequency that we read the sensor during one sampling period. Later, I guess Joeri will explain about the sampling period, which for our system is, I think, every 3 minutes. But this sampling rate is how many times each sensor is read when we start sampling for one sampling period. Then the signal from the raw signals, the digital output or the analog output are then averaged from these multiple samples, and the microcontroller format them in a standard CSV string and puts them in the buffer of the UART and puts the data in the UART buffer and communicate to the rest of the system. So that's the algorithm, how the behind the sensor shield and reading of the sensors. Another important part, as was mentioned in the presentation of Marianne also, is the calibration of the sensor. So as I mentioned, all the sensor shield provides raw data. So simply the voltages from the analog sensor or the digital signal from the digital sensors, but completely raw data. In order to convert this data to these raw signals to meaningful gas concentration, we perform series of calibration of the sensors, where the sensor were exposed to known target gas concentrations in controlled environment, and the output of the sensor was read, and we were trying to obtain the calibration model for each of the sensors. So on this slide, you can see the approach that we took for the sensor calibration. So each of the sensor was exposed to the target gas following this this pattern. So for each target gas, we developed at least 4, in this case 5, concentration levels of the target gas, and the sensor was each box was exposed to these concentrations at controlled temperature and humidity in the exposed chamber. So in the next slide, those are the chambers that we have at V2 for performing the tests, and we used. So we have on the top left corner, this is our chamber for gas generation. We also have the chamber for particulate matter generation, temperature controlled chambers to perform all of these tests. The gas concentration, another important thing for us was to compare the output of the sensors and calibration and conversion of the signals with reference instrument, the instruments which are widely accepted for measurement measuring gas concentration in indoor and all kind of environments. So in this case, these are the reference instruments that we used for following the concentration inside the sensor test chambers during the exposure of the sensors at different concentrations. And here, yeah, slightly, just a small part of our calibration models that we obtained for yeah, the temperature sensor, for CO2 sensor, some of particulate sensors, but yeah, more detail about this, I think Olivia will present a bit later for the outcomes and the models of calibration. So, Joeri.
Thank you, yeah. Boris. So Boris has given a small overview about the Elgas sensor shield. I will go briefly into detail about the processing part. So for the processing part, we have selected a single board computer. One of the requirements is, of course, the availability of a UART connection. So this single board computer will read out the data from the UART buffer. But the data is read from the UART buffer and will be sent to the cloud. So the software is written in Python. So we have used a multi-threading approach, and each thread is a process in our let's say data pipeline that is running on the Raspberry Pi. So we have, of course, 5 threads. You have your main thread, of course, and then 4 threads. The first thread is the sensor thread that will read out the UART buffer and send out the data to the cloud. Then we have a second. The second thread is the where you will send the data to the cloud. And then we have a third thread that does the translation from raw data to calibrated data. This calibrated data will be stored in thread 4 into a database, and also this database is used for the data visualization on the display. Then we have a second part in our system, a third part in our system, that is the communication. For the communication, we have selected a commercial off-the-shelf solution. It's a combination, of course, of an antenna and a router. We have selected the antenna and the router in such a way that we have the coverage of the different communication channels that we use, GSM and 3 and 4G. And also there is also a GPS on board of the router to collect the location information. This is a small example of a small result of one of the measurement campaigns that we have performed during the Elgas project. This is the measurement campaign of the Erva Belgica in March of this year. On the top, you see the GPS data from the sensor box compared to the GPS of the Erva Belgica. So in blue are the GPS data sampled every 3 minutes, and in red is the data from the GPS of the Belgica every 10 minutes. In the bottom, you see the comparison between the data from the cloud and data that is stored on the SD card. This graph shows you the raw data. The second main part in our Elgas platform is our cloud environment. The cloud environment has mainly 2 functions. First function is, of course, the visualization of the data, but also the second is the data storage. So data from the sensor box is stored in the database in the cloud, and we have built the necessary components to get access to the data. So we are able to download the data into, for example, a bundled data frame, and this data can become an artifact for an input of a component in your data processing, pre-processing, post-processing pipeline. For those who like to get some insights about the electronics and the use of the Alting Stock API, we have prepared a small tutorial that is also available online. So for those who like to play around with some hardware, to play with the Altix Talks Maker Cloud Platform can have access to this tutorial and follow the necessary instructions and get some insights in your air quality. Okay, so now I will hand it over to Lawrence and Gustavo that they will tell you more about the data visualization and the algorithm.